did the dances for +1, +2, and +3, and here are the distances. Now we're like a broken record. We just keep repeating the same pattern. The denominator is simply n minus 1. The numerator corresponds to the number that we plus. It is 1 for +1, 2 for +2, and so on. Then we multiply this quantity by the value from step n minus 1 to obtain the value for step n. Notice the positive input produced no rotation, and the negative input produced a 1/2 rotation. But it kept everything on a straight number line. So is +1 and -1 the only dance options that we have for distance 1? What happens if we follow the same recipe for distance 1 as the input, but then we only rotate 1/4 of a turn rather than no rotation or a full 1/2 rotation? Call it the 1/4 rotate 1 dance. Now the distance should be the same since it is still a 1 dance. But now we rotate, which means we rotate 2 dimensions. So north-south to go with the east-west. We're back on our dance floor where we've got the same number line that we've got going here. We can call that our east-west line. And now we're going to make this 2-dimension, and Carolyn's going to walk down our new dimension, and that's like our north-south number line, and this gives us 2 dimensions. And so now let's do a dance, and we will start the same spot we've always started, which is at the origin. And the first step was the same one that we had before, which was a distance 1, and it was in that direction. But because we're multiplying by I, you notice Carolyn rotated. And that's getting her ready for the next step, which we're taking the same distance, which is 1, but now we're going due north 1 unit. And because we multiply by I, she rotates again. And now she comes back a 1/2 step here. And that's where the point she lands. And then now she takes another step there, and she takes 1 more step. And if she did this an infinite number of times, after she'd get dizzy rotating around, she would end up approximately at that spot she's at here. Including a 1/4 rotation seems like a natural next step after a 1/2 rotation. But can we think about this in math terms? Remember, multiplying by I produced a 1/4 rotation in the complex plane. So we can think about our +1 with 1/4 rotation as I times 1. And then what we're calculating is the result of E raised to 1 times I. And that means that our plane is the complex plane where north-south are multiples of I. So that means our ending point on the complex plane is 0.54 and then 0.841 times I. And remember, we can write a point on the complex plane as a number. And so we can create an equation that says E raised to the I equals 0.54 plus 0.841 times I. And this is because the vertical axes in the complex planes are multiples of I. Now, it does seem like an odd equation, but it makes sense when we think about it in the complex plane. So let's try entering 2 times I as our input to calculate E raised to 2I. We're now ready to input 2I into our equation. And as you can see, we left the dots in the 1I so you can get a perspective on where those points landed in her dance steps. And now we're going to input 2I, and we'll start at the same 0, 0, and we're going to take the same step 1 that direction, take another quarter turn. This time we're going 2 north, and then take a quarter turn, and we come back this way 2, and we come back this way 1, and now another rotation, and we continue to turn and rotate, and after an infinite number of times, we're going to land on this circle. And as you can see, this is our unit circle that we've got, and we now land on a different point than we did before, but still on the unit circle. We found that entering 2I into our formula, we finish at the point -0.416 and then 0.909. In the complex plane, this is the point -0.416 and -0.909I. And that means that we can say that E raised to 2I equals 0.416 plus 0.909 times I. Okay, let's try one more. We've entered positive and negative integers. Also, we've entered positive integers times I. So let's try something strange and input pi times I. Now, pi is not an integer, and so far we've only entered integer values. So what happens if we input pi times I? What we're solving for is e raised to pi times I. And how weird is that? I mean, raising any number to an exponent, p times I, doesn't seem to make any sense. It's like we're scrambling all these cool things together, throwing it at a wall, and hoping it sticks. Now, even though this expression doesn't seem to make much sense, we do have a way to calculate it. And remember, our pattern is the distance that we travel in step n is the distance we traveled in the previous step times x divided by the quantity n minus 1. And now we're just letting x equal pi. So we can calculate it. But what could it actually equal? We are now ready for our grand finale, where we input this weird number pi times I into our equation, and Carolyn is going to start at the same spot. She's going to follow the dance routine she did before and rotate every time with the distance, and the first move will be to the same spot, 1, 0, and then she's going to continue, and let's watch this happen. Wonderful. And notice where she ended up, right on the point -1, 0, and that's where she ended up on the unit circle. And it may seem odd that we landed on an integer value when we input something strange like pi times I. So you wonder, why does that occur? There's actually a good reason for that. And the reason is that the distance on our unit circle from this point, if we travel around here, is exactly pi. Because if we kept going all the way around, it would be 2 pi, and if we stop halfway around, half of 2 pi is pi. And that's not the only thing that we've got that's a pattern. If we start here and we just go 1 unit around the circle, we end up at this point right here. And remember, that was the point where we input 1i into our formula. And if we travel 2 distances around the circle, we end up exactly at this point. And remember, we input 2i into our equation, and we ended up exactly 2 units around the unit circle at that point. And so that's the beautiful pattern in all this, as that when we input pi I in here, we're going to end up on the unit circle exactly pi units around, which is at the point -1, 0. This was a fun exercise, but I kept the math to a minimum. But if you want to dig deeper into the math, here's a link to a couple of stories from Lazarus Math where you can whet your math appetite. Now, the math can get a bit intense, and normally this math is presented with a lot of notation that could make it difficult to digest and understand. But using our little dance pattern, we took a different approach, or viewed it from a different perspective. And the cool thing about these patterns is that even though each step may look random and not going anywhere specific, in the end, we landed on something meaningful. And it was especially neat when we used the imaginary number I as an input, and then we traveled off the number line and into the complex plane. Now, it appeared we were wandering around, but by keeping to the pattern, we arrived at a specific destination, a place on the unit circle. Well, math can be like life. Both can be messy, where things don't make sense, and sometimes we feel like we are wandering around without a purpose or a hope. And when we're stuck in math, trying harder doesn't necessarily work. Our solution may require a new perspective, a new angle to consider. Or perhaps you're stuck in life and trying harder is not the answer. I know I've been stuck in life where trying harder did not help. What I needed was a new perspective. I needed to see that my life is not random, but it has a purpose. It is part of a bigger pattern. We believe that our lives matter and have a purpose, that there is a direction that we can go that arrives at a special place. And Brian has some words of hope that can help you navigate to a better place.